Math problem. A prince is staying at the castle of a beautiful princess. She decides to play a game with him. Here are the rules. The prince has to find the room the princess is hiding in. The prince is allowed one guess per day. The princess will never hide in the same room 2 days in a row. She will every night move one room over to the left or to the right. The princess promises the prince a special treat if he finds her. The prince, who is currently taking ENCMP 100, decides to write a program using MATLAB that will solve this puzzle. The major objectives of the program are as follows. Develop a program that will solve the math problem for any number of doors, create a simulator to test the solutions generated. A good starting point for this program is the simulator, because it's the simplest to write, and programming it may lend insight into how to solve the problem. The first version was only 20 lines of code. It allowed exactly 4 doors to choose from. The princess starts on a random door, and she hops around left or right randomly, unless she is at an end door. Then she only has one choice of doors to move to. From there, it's pretty simple work to expand to a user input number of doors. Well, that was pretty simple. Later we'll add a multiplayer option with user and computer player modes. The computer will use our game solver to make the best possible moves. Now it's time to look at how the problem works. The first night there are 4 possible locations of the princess, and each is equally as likely. The next night, for each door that was a possibility the night before, she can move in either of 2 directions, except for on the end doors where she only has a single option. The goal is to find a series of door selections that will narrow the possibilities down to a single door. This is the fastest option for 4 doors, which can be worked out by hand easily enough. But a solution is much more difficult to find when the problem is expanded to 5, 6, 7, 20 doors. Hence the program. The steps the solver program will take are: find possible candidates for a solution and test possible solutions for fastest route. A large portion of the possible solutions are obviously ineffective and can be ignored right off the bat. Here's where a better understanding of the problem will help in writing a better program. So first, a series of door choices is invalid if it chooses a door 3 nights in a row, because the princess can move to a room and back again, and you're worse off than when you started. Next, never choose an end door. The possibilities springing from end doors are much smaller than from other doors. Choosing other doors will always be a better choice to deleting possible princess locations. And lastly, the problem is symmetrical, so we can immediately ignore half of the doors on the first move. That looks pretty good, but knowing the growth on these algorithms is quite large, let's test for a large number of doors. It took a long time, even though we were smart about our choosing algorithm. The problem is this: the fact that we don't know how big the next night's array is going to be, and the way the code was written, makes it difficult to pre-allocate. Because we're only adding a couple lines at a time, doing that millions of times over takes a really long time. So it's a problem. But because of the versatility in programming, there are almost always many ways of doing something. This is true at all levels of the program, from how to construct a while loop, or whether you should use a for loop instead, or maybe you should look at options outside of a loop, or maybe the structure of the program should change, or sometimes you might not even need the script you're writing at all. Because of the extreme flexibility in programming, a good programmer should try to be flexible himself. The lengthiness of the execution was a problem, and the fix to the problem seemed a bit time-intensive. A flexible programmer keeps in mind other possibilities, besides trying to boulder through every problem that arises. Keep in mind ways to sidestep the roadblock. I went back to the simulator and updated its features, including turning the script into a function so you can't see the location of the princess in the workspace, and adding in a multiplayer option with a sub-function ready for the computer player's playing algorithm. After writing the program to test our possible algorithms, here are the results. The results for 4 nights, good, that's what we worked out. For 5 nights, 6 nights, 7 nights, 8 nights, wait a second, there's a pattern. The solution is iterative. Iterative solutions are a programmer's best friend. The computer's real strength is the ability to do a process really quickly. Look for solutions that use the same bit of simple code over and over again to save on code writing time, and get the computer to do the heavy lifting for you. This iterative solution turned this program, solving for 9 doors, which I aborted after half hour of running, into this program with a runtime of 0.005 seconds. As a side note, the run end time function is a pretty handy tool. It breaks down the execution and tells you how much time was spent in each block of the code. Interesting to note is that out of the over a half hour of runtime, only 5 seconds was spent in the inefficient code I was worried about. Not worth trying to speed it up. Look for other solutions. Stay flexible. To finish off the simulator, we completed the auto-choose subfunctions, added in some checks so that only valid inputs by the user would be allowed, refactored some of the formatting, and threw in some graphics and sound to make the program a little more enjoyable to use. Because of our limited MATLAB experience, the graphics were generated externally and saved frame by frame as images. These images are then called successively at a set rate to mimic video playback. And that's it. Here's the final product. The probabilities are available in a file generated by the solver, so you can find strategies of your own in case you yourself ever have to find a princess. Enjoy.